Most of you know who I am, but for those who don't, my name is Zubin Kabraji. I am the secretary of ALUCAST and one of your co-hosts for the day. Uh, uh, we had uh, we had excellent sessions yesterday. Uh, Tremendous takeaways in terms of knowledge. And I think we are indeed indebted to all the speakers and presenters for giving us so much useful information. Uh, uh, I'm sure that we'll have a similar run today with equally informative presentations. Uh, First on my agenda today is the launch of the technical volume of the conference. And I will be requesting our special guest for the day, Mr. Kaushik Manna. He's the Chief Operating Officer of Rockman Industries to release this publication. Samita, can I have the report on screen, please?
Sure.
There we are. Mr. Manna, can I request you to declare this technical volume as launched?
Yeah. Good morning, everyone. So this is my honor and pleasure to declare this technical volume as launch.
Thanks, Mr. Manna. Right. Copies of this technical volume will be received by all registered participants on a pen drive. Pen drive specially prepared for us by Raga, the Raga group. Thanks to Mr. Rahat Bhatia. Let's move on. Let me now introduce you to our special speaker. Just let me diverge for a moment. I'd just like to welcome Mr. Ujjwal Munjal of Rockman Industries. He's been one of the pillars of this conference. Thanks to him, we are using this virtual platform, which has been provided by Rockman Industries. Thank you very much, Mr. Munjal. Pleasure to see you here this morning. Let me now introduce you to our special speakers. Kaushik Manna completed his Bachelor of Engineering from Bengal Engineering College, Sipur in 1996, and he has over 25 years of professional experience. He did his postgraduate diploma in business management in 2003 from Symbiosis, Pune. He has worked in the field of aluminum during the major part of his career. He joined Rockman in 2012. Prior to that, he worked with Hindalco, Endurance, and NCAT. He has experience in almost all the pillars of operations during the last 25 years, including quality, WCM, product engineering, greenfield projects, manufacturing, and much more. Ladies and gentlemen, without further ado, I give you Mr. Kaushik Manna, CEO, Rockman Industries. Sir, the stage is yours.
Thank you, Zubin, for your beautiful introduction. Good morning, all, and a warm welcome to all of you. I would like to start with a quote by Albert Einstein. If you always do what you always did, you will always get what you always got. So what does it mean? Change is the only constant. So if you want a different kind of result, you have to do the things differently. I am honored to open the second day of this virtual conference by ALUCAST with Rockman Industries as a principal sponsor. I hope all of you gain something from this today event. I am pleased that this virtual conference has received so much support. ALUCAST has always played a very important role in bringing you all excellent program in training and technology, and will continue to do so. We all are aware how COVID-19 has taken its toll over the last 12 months across the world and also on the industries. This was also shared by ALUCAST trustee Mr. T. Parabrahman yesterday. I completely agree with him that human resilience is slowly but surely beginning to prevail as we are now pulling ourselves out of this crisis. If this is to be the new normal, then we are mastering the art of it during the past 1 year. But I can assure you that this will be an ever-changing scenario. The only way we can navigate these times and continue to grow is by staying a few steps ahead through the use of best technologies that are available and encouraging everyone in the organization to be prepared for the change. As you know, necessity is the mother of invention. And this COVID pandemic has created that necessity for us today. Crises do not hinder the innovation, but it makes it more relevant and necessary. This is exactly what is happening in our industry today. Innovation will impact the way in which we produce the aluminum die casting. Some will quick, others will take time, but change due to innovation is inevitable. Event like ALUCAST will help spread these new ideas among us to help us grow together by implementing them in our respective organizations. In my own organization at Rockman Industries, we have laid great emphasis on technology and training. Almost without fail, we have participated in NADCA training schedules when they have visited India. Last year, ALUCAST even planned a dedicated program for us with them. And that was a great success. These learning events have helped our team develop new skills and disseminate innovative ideas to the shop floor. As we commence day 2 of this program, I would exhort all of you to share your best practices with ALUCAST so that the entire aluminum die casting fraternity can benefit from this experience. At the last, let me add my thanks to everyone who worked on the conference to make it a success. Even though virtual event seems easier to plan, the effort that goes into such planning is no less than a regular conference. I hope you have a good interaction and learning on day 2. I wish you all success for the future. Be safe. Thank you. Over to you, Zubin.
Thank you very much, Mr. Manna, for those encouraging words early in the morning.
Frozen.
Yes, this event will take home a lot of learning. Let's move into the session. Even though we are 5 minutes ahead of time, I think that's just as well. Let's move into the session. The session chairman for the day to start off with is Mr. Tej Bamra. Mr. Bamra is a member of our Delhi Center Committee. He's a part of Rockman Industries, and he was with us yesterday, also did an excellent job of keeping to the schedule. Mr. Bamra, the floor is yours.
Thank you very much, Mr. Zubain, and also thank you to Mr. Kaushik Manna for his, words of wisdom. And a very good morning to everyone. I'll be your session chairman for the next two papers until 12:05 today, and it's a pleasure to, share with you the first paper, which is on the improved melt quality for high integrity aluminum castings and critical melt treatment practice and melt quality analysis for aluminum foundries, presented by Dr. Philip Kansler, International Marketing Manager of Foseco International Limited. The paper speaks about the HPDC as the preferred method of making aluminum castings. Cost savings and inclusion removal can be successfully achieved using MTS 1500 and VMET melt quality assessment. Oxide removal is the most important step in improving melt quality, and MTS 1500 together with VMET melt quality assessment has made a significant contribution in aluminum pistons, wheels, and chip remelting. As regards to the presenter, Dr. Philip Kansler is a MS in metallurgy, mineral processing, and powder metallurgy. He is associated with Foseco non-ferrous group for over 16 years, with postings at Shanghai in China, Kobe, Japan, Tamworth, UK, and Launes in France. He has contributed in the upgrading of the rotary metal treatment station to eliminate the drawbacks and provide consistent metal quality with improved productivity. In this paper, he would explain about some of the salient points of the treatment. So it's over to you, Dr. Kientzler. It's a pleasure to have you on board. And you will have 40 minutes for this paper, including 5 to 10 minutes of question and answer sessions. So we begin the session now. Welcome.
Thank you very much, Mr. Chairman. Can you hear me?
Yes, we can hear you.
Okay, thank you very much. I'm very honored, and I want to thank ALUCAST for accepting the paper. It's a first time for me to present a paper in ALUCAST. I also want to recognize my co-author, which is Mr. Shrikant Bhatt from our company Foseco India. I have been working together with Shrikant for almost 10 years now, and we've had many, many successful projects across India and other parts of the world. Just one question is, am I showing the PPT or are you showing the PPT?
We would request you to show the PPT. We are not able to see it right now.
Okay. So let me try, because I haven't tried this before. Let me see. Can you see the PPT?
Philippe, go to the bottom of your screen. You'll see a green button. You say share.
Yes. Okay, I remember.
Yeah.
Okay, yes. Share the screen. Okay, yes, I remember. Okay. Very good.
Excellent. Now you can click on your presentation and take it to full screen.
Now I can take it to full screen. Yes, very good. Thank you very much.
Yep.
You can see it now?
You're ready to roll.
Okay, thank you. Thank you very much, Mr. Chairman. Thanks for the introduction.
Yeah, we can see it.
Sorry? You can see it.
Please go ahead. We can.
Okay, thank you. Thank you very much. So in the last 10 years, I've lived in Asia, China, Japan, and I've been traveling across most Asian countries looking at foundry practice, improving melt quality, supporting our local teams, in removing some defects or developing some new products. So I've summarized some of the projects I've done in the following paper. And we are not going to review everything because that's in the paper, but I will run through some of the key points that we have found about the key benefits of the technology, but also about what we call VMET, which is our new metallurgical assessment of melt quality, because more and more today's foundries want to know how good their melt is. And they are looking for tools, to evaluate the melt quality either before casting or in the melting furnace. So this is a very important step, and I will review some of the important things we have done in high pressure die casting, but also in low pressure wheels, as well as in chip melting, for instance. So first of all, most of you, I hope, know now about MTS, this technology.
So Mr. Kientzler, sorry to interrupt you, Mr. Kientzler.
Yes.
Yeah, you will have to switch your cameras. What you have to do is go to the display settings and duplicate.
You want to see the camera?
No. You have to, we see both your screens, the smaller one with the slide and the larger one with the presentation.
Okay.
Just go on your settings, display settings. On the top left, if you see, there is a display settings. On the right?
On the right.
Right of this, you have a display settings.
In the center, display settings.
Yeah, just
in the center.
Just right of your cursor, where you've got your cursor right now. If you go just right, you see display settings mentioned there.
Where is that?
Just next to show taskbar.
Yeah, this one. Yeah.
No, wait a minute. Sorry. How does that work again?
Philip, we are seeing your.
No, I know, but this is I'm not used to Zoom, so
No, on the top, second input is display setting, show taskbar and display setting.
But I don't. Where do you see that? Down in that menu?
No, on the top.
On the top, show taskbar.
And to the right of it.
To the display settings. Okay.
Yes. Yeah.
So swap presenter view and slideshow.
Yes. Or duplicate.
So now you can see my.
We are seeing the full screen. Yes. We are seeing the full screen.
Yeah, okay. Sorry for that. So, thank you very much, Shrikant. So, about 15 years ago, we developed this technology called MTS 1500 Metals Treatment Station, okay? And we've been quite successful because this technology enables every kind of foundry, whether it's sand, gravity, low pressure, or high pressure die casting, to see some kind of benefits. So in the early days, the benefits were cleaning and drossing. And these are examples from wheel foundries, low pressure wheel foundries making OEM wheels. Very quickly, we moved into more difficult application, which is titanium boron grain refining, for instance, which is a very important process, both in gravity and also in low pressure wheels, for instance, because it has a big impact on elongation, on UTS, on mechanical properties of the casting. So nowadays, we are able basically to use this technology for some kind of benefit in almost every segment of the aluminum foundry. And last but not least, our latest work has been in die casting, so high pressure die casting, which was always perceived as a less stringent or less critical area. But we find out nowadays that more and more high value castings are made with the high pressure die casting process. So the control of quality and the monitoring and achieving higher melt quality, even if it's not degassing, but let's say achieving better cleaning, removing oxides and inclusions, especially intermetallic inclusions that can lead to hard spots. These are critical points that high pressure die casting foundries are having to address these days. So just to quickly remind, MTS is based on a rotary degassing. Okay, in the early days, this is an example. You know, we were achieving very good degassing in 4 minutes. This example taking from some lab experiments that we had done. I think there is no discussion anymore in the industry now. Rotary degassing was proven, and most industries now are successfully using rotary degassing, you know, to improve the quality of their castings, even in high pressure where gas is normally not a problem. How did we achieve that? Foseco has several R&D centers in the UK, in Germany, in USA, and we've done a lot of work to try to better understand the degassing and the degassing performance. So here is an example we did in our lab in Germany. We have a 500 kilo crucible, and where we are able to do live experiments and live treatments on real melts. And in the early days, we had our standard rotor, which is called SPR, which is the blue one. And you can see here plotted how the hydrogen content will vary over time during the degassing process. Here, typically, we're showing 4 minutes of degassing. Now, because we've done a lot of R&D and work internally, we've developed the rotor, which we call XSR, which is shown there. And you can already see is that that rotor will drop the hydrogen level much faster than the standard rotor. So this is an improvement in terms of the degassing efficiency. And today, the XSR rotor, the red one, the red curve, is the standard that we have in our customers and in many parts of the world, including in China, for instance, where I have spent a considerable amount of time. But we continuously need to develop new technology, you know, and improve the performance. So in the last decade, we've been working on a new rotor called FDR. This is the yellow curve shown there. And you can see that this new rotor is enabling to further degas much faster and to much lower levels than was previously done with our standard rotors. Now, this may not be needed in every industry. It may not be relevant, you know, in high pressure. In high pressure die casting, most of our customers are happy with XSR because degassing is not the main issue they're facing, you know. So we have other things to worry about inclusion, oxide films, hard spots, and hard inclusions, for instance. But in terms of degassing, FDR now will be in the future our best-in-class product for those foundries who worry very much about the degassing. So we moved then to some different applications. You all know that in the past, mostly in sand and gravity, sodium was used to modify the eutectic structure of our aluminum silicon alloys. Now, nowadays, many foundries have switched to strontium, and strontium is recognized as the better way of modifying most castings, whether it's wheels in low pressure, whether it's cylinder heads. Most of the people in the industry use strontium, but there are a few applications which remain with sodium, because when the cooling rate of the casting is not sufficient, when you try to use strontium modification, you sometimes have shrinkage, residual shrinkage that the foundries cannot get rid of. And for those reasons, I know many foundries around Asia and around the world who are still using sodium because sodium is a much stronger modifier than strontium. And here is the case, but the problem with strontium is it was expensive and you have to use a lot of sodium. Sorry, with sodium, you have to lose a lot of sodium. You have to use a lot of flux. So we've developed some application where basically we can reduce the addition rate of the sodium. And in this typical case, which is shown here, we go from 0.3 to 0.1% addition using our MTS process. Okay, so for the foundry, they will get the same quality, but there's going to be a significant reduction in cost in the addition of the sodium, in the addition of the flux. So this will be a benefit for those foundries. And in Europe, in Germany, but also in China, we have some customers who are still using sodium for this specific application because they cannot get the same level of quality with strontium. Then we did some investigation to further understand this. And again, we went back to our lab and to our 500 kilo crucible, which we have in Germany, where we are able to do a set of experiments. And what you see here is we increase the amount of flux used on the x-axis, anywhere from 200 to 1 kilo of flux of a sodium modifier. And we measured the sodium pickup that we have in the melt. And what you can see is that if you use this MTS process, basically the sodium pickup for the same parameters, the same crucible, the same condition, the same alloy, everything else being the same, the sodium pickup is about 2 to 3 times higher when we use this MTS process than when people use the traditional method of introducing sodium. So again, many of these foundries in Europe, in Germany, in a few in USA, but also in China, we now have customers who have moved away from the traditional sodium process to our MTS process because basically they're getting higher yields of sodium modification. Now, this means either better quality for the casting, less shrinkage, and a much finer eutectic structure, or it means less sodium use, so it means a lower cost for the foundry because they can reduce the addition rate of the sodium or the sodium flux. So again, this has been an important breakthrough for us. Then we moved into grain refining. And all of you know that in sand, in gravity, and in low pressure, titanium boron grain refining is a very important part of the process. And especially when you do safety components, you know that the mechanical properties, whether it's elongation, whether it's UTS, are directly correlated to the grain size. Of course, there are other things. There is oxides. There are other parameters that will affect these mechanical properties, but grain size is a critical factor if you want to make wheels, if you want to make certain safety components, suspension, transmissions, and things like that. So we had a lot of success in gravity, automotive foundries, or suppliers who make suspension, knuckles, for the automotive foundry. And here's an example from one of those foundries where you see the grain size before. So this is a sample solidified from the melting furnace before grain refining on the top. And you can see the large grains. And on the lower side, you can see after addition of 0.04%, which is much lower than the normal Tibor grain refiner, you can see the structure we get. So many of these gravity foundries have switched from master alloys, and I'm showing here a little calculation and a cost evaluation we did a few years ago in Europe with one of those foundries, and where we compared. So they were using roughly 1 kilo of Tibor master alloy per ton of melt, and we were able to reduce this to 400 gram because our grain refiner has a higher percentage of titanium boron. So we are able to reduce the addition rates, and we are able to offer a much stronger grain refining and achieve a much finer grain than what they would otherwise achieve with the master alloy. So for those foundries, there's two advantages. One of them is a finer grain, better mechanical properties, and a cost reduction because of the reduction in the flux compared to the master alloys. So those foundries who are using this process have completely stopped using the Tibor master alloy. So this is a significant saving for the foundry in terms of purchasing, okay? So not everybody's using it, but I think more and more foundries nowadays are doing this kind of comparative work. And it doesn't always, have the same outcome. It really depends on the requirement of the foundry. Those foundries making safety components, those foundries making critical components will see a benefit in this. Of course, if you make very general castings, non-automotive castings, maybe the master alloy will be good enough. Maybe this is not necessary. This is for every foundry, basically, to evaluate and to decide for themselves. After that, we moved on to a much more challenging segment, which are the aluminum wheels made in low pressure. And as you know, this is a very important in India, in China. There are hundreds of millions of aluminum wheels made, OEM wheels made for the cars every year. And these wheels are safety components. They have to be exempt of gas and shrinkage. We cannot tolerate oxides or inclusions, especially if they're above a certain size, because they will reject the wheel. They will lead to premature failures. And of course, we need a very fine microstructure in order to get the mechanical properties. So this is an Asian automotive wheel foundry, a very large group, which has many foundries and many low pressure machines. So their traditional process, and you have the parameters summarized here, they were using a 700 kilo ladle in which they were adding 500 gram of master alloy and then doing a 9-minute rotary degassing treatment before transferring this A356 alloy into their furnace. So we introduced our new process side by side with their traditional process. So the ladle's the same. We completely removed the master alloy and we added only 310 gram of our new titanium boron flux grain refiner, which comes out to be 0.04% addition rate. We kept the degassing the same. So all other parameters are the same. Then the foundry did some wheels. They cast the wheels. They took some wheels. They looked at the density to make sure everything was comparable. They looked using the spectrometer. They looked at the titanium pickup because they wanted to make sure that if they switch from a traditional Tibor master alloy to our product, they wanted the titanium pickup to be in the same range. And you can see here, they had the same range. They made a certain number of wheels, which they heat treated using the standard T6 heat treatment. And then they took samples from the spoke, from the hub, and from the rim of those wheels. And they measured the DAS, because even though DAS is not directly related to the grain refining, DAS, dendrite arm spacing, is a critical parameter of the wheel manufacturing process. And in modern wheels, in modern OEM wheels, you need a DAS which is smaller than 50 micron. And I'm only showing this because this, for the wheel foundry, was a way of checking that the wheels that they were making with our new process, you know, were within the specification. You know, if the DAS for some reason had been higher, they would have rejected the wheel. They would have said something is wrong, okay? So the DAS measurement here is only a way to check that this wheel is within the specification that this wheel foundry has. And so we looked at the results, and here is a micrograph taken from the spoke of one of the wheels, and you can see the structure is extremely fine. This is a picture they did in their lab, and they measured the DAS, and they looked at the structure, and they also measured mechanical properties. And this is where we saw some very interesting things. We saw that the average elongation they had on the wheels when they're using their traditional tie-bore master alloy process is given here to be 6.8%, okay? And in all the wheels they did with our process, with our new MTS 1582 process, the elongation jumped up to 8%. So even though they are within specification, they saw an improvement of the mechanical property of the elongation, which for wheel foundries is critical. When they looked at UTS, yield strengths, tensile strengths, they saw exactly the same thing. They saw an improvement. Sometimes it's a small improvement. Sometimes it's a more important improvement in percentage. So this enables me to say that our Coverall MTS 1582 is a far more efficient way to grain refine wheels, OEM wheels that are made in the low pressure process. And this we were able to prove, and this foundry, as well as many other wheel foundries in Europe and a few of them in Asia, are now switching from the tie-bore grain refining, from the tie-bore, master alloy use to our MTS 1582 grain refiner for these two reasons. The first reason is the improvement of the mechanical properties, which we were able to demonstrate. And the second one is the reduction in the addition rate, which you see here, 0.07% for the tie-bore and 0.04. So for the foundry, this will represent a saving because they will have a lower cost when it comes to grain refining. So this is a very important aspect for the for the wheel foundries, and we are currently extremely busy going to many wheel foundries where we are doing trials and where we are let's say expanding our experience with this product to many automotive wheel foundries across Asia. So enough for gravity and low pressure wheels. We need to talk now a little bit about high pressure, because as I mentioned in my paper, nowadays 50% of all aluminum castings in the world in tonnage are made using high pressure die casting. So this is becoming the most important process in the aluminum industry, high pressure die casting. And in the country where I'm currently located, which is Japan, we know that 70% of all aluminum castings made in Japan are now made by high pressure die casting. So there is a clear trend that the castings are moving from gravity and low pressure to high pressure die casting. There's a real motion, and this trend will continue in the future. So we need to be more focused on high pressure die casting. So I visited a number of very large automotive high pressure die casting foundries, and this is the example of the work I have done in one. So in this case, this is a supplier to the OEMs, to the Japanese and Chinese automotive foundry. And they are using very large capacity ladle to transfer the melt from their melter to their casting furnace. So 1.4 ton. This is a very large, and you can see they're doing 180 ladles a day. So this is a very high productivity, very high intensity, high pressure die casting. So we looked at their standard process, and quality wise, they were very happy. They didn't have any special rejects, any special issues. But when we looked at the dross on top of their ladle, we saw that the quantity of dross that they're generating during their melting and processing is extremely large. And we, as you can see on the picture below, we invested in a number of steel buckets, which we used to collect the dross from many ladles that are being processed in that plant. And when we averaged, we discovered that on average, when they transfer the melt, they have 4.7 kilo of dross, which is generating on top of every ladle when they transfer from their melter to their casting furnace. We send a sample of that dross to an outside lab, and the result came back that this dross contained 86% of trapped aluminum. So this is not oxide. This is aluminum droplets that have been turbulent, that have been trapped in the dross and are still aluminum in the dross, okay? Now, we gave this foundry our new MTS process side by side with their original process, and we did a comparison, we did a benchmarking, because we said there has to be some saving in your process, and we want to help you achieve this saving. So they did a number of processes with our MTS 1500 technology. We collected the dross, we averaged the value, and you can see there with our process, the overall dross quantity is around 3.5 kilo per ladle. And we send that sample to an outside lab, and the analysis came back 43% of aluminum is trapped. In other words, our MTS process is able to remove valuable aluminum from the dross before you remove the dross from the ladle. So this is a huge saving. So I have calculated there 2.5 kilo, 253 kilogram of pure aluminum that was trapped in the dross in that foundry. We are able to save, okay? When we multiply this by the number of ladle that this foundry is processing, this is a very large high pressure die casting, it represents 136 tons of aluminum potentially saved. This is a huge number, and we didn't change anything else. The processing time is 3 minutes. The temperature of the melt is the same. So all we did is, rather than use their standard HPDC process, we took the ladle and we used our standard MTS process. And the result of that is a saving of 136 tons, which when I calculate at LME prices is more than $250,000 per year of saving. So this, for high pressure die casting, is a huge saving for no extra cost, So we now have many foundries in China, many foundries in Asia who are looking at this technology and who have already invested in these technologies just for saving aluminum in the dross, because this is a huge cost saving for them. So let's talk a little bit about the second part of my paper, where I am combining a new technology called VMET, which is our proprietary technology, which we are using to assess the melt quality, to try to benchmarking the melt quality. So we're using a copper mold, which is used in grain refining. People who do grain refining sample, usually use a copper mold. So this is something we have in our lab. We take a sample from a melting furnace, from a ladle, from a casting furnace, from a crucible, and then we section the sample, we polish it as you see here, and then we use our SCM and EDS to analyze. Basically what we are doing here is we're able to look at the structure with a scanning electron microscope, and the EDS is a spectrometer that can analyze the chemical nature of the features. So is it an oxide? Is it magnesium oxide? Is it an intermetallic rich in iron, for instance, in high pressure die casting? Is it a pore? Is it a bifilm? Is it a hardened inclusion? So this technique enables us to identify in a given sample any pores, any oxides, any non-metallic inclusions that can lead to defects. Now, this is very important because it tells the foundry something about their melt quality. You know, it tells, before you start casting, before you turn on your robot, you want to know how clean is my melt, how good is my melt, is my furnace ready, or is it very dirty? So by taking this sample, we are able to help foundries, give them some kind of a quantitative. Now, why do I say quantitative? This is because this software we develop is going to scan the sample and is going to count all of the defects that are found. So all of the oxides by nature, by sizes. You can see here that these defects, aluminum oxide or inclusions, will be classified by size, by nature, and by chemical composition. And so, sorry, what we know from experience is where if you have an oxide smaller than 15 micron, usually it doesn't give a defect in a casting. I have never seen in my 20 years in Foseco a casting that was rejected because of a 10 micron oxide or inclusion. But what we know is when the size of these oxides increase, so typically the yellow range there, 75 micron or larger, this is when we start having leakages. This is in certain castings. This is when we start having castings who break, castings where we have cracks, castings who are not gas proof, not pressure tight, because there was some oxide or some porosity in the casting. So this tool is a very interesting tool to try to map and to try to benchmark the melt before we actually make the casting. So about 10 years ago, we went to a very famous European wheel foundry, which is using low pressure A56 alloy. And we took a VMET sample of the melter, which is the column A56, the white one. And you can see we have found, and that's normal in a melter, you know, when you melt ingots, when you melt chips or scrap, you create a lot of oxide. So this is expected, okay. Then the foundry has some kind of rotary degassing machine, not using flux, simple rotary degassing. So they process the ladle, and after treating the ladle for 10 minutes, that's the yellow column, we took again a sample, which we did a VMET analysis, and you can see a dramatic reduction in the number of oxides that we found, in the number of inclusions. And more importantly, the last line, the features bigger than 15 micron, which are a real concern, those that will lead to rejected castings. You can see a real reduction. So this is a very nice proof that for those people who don't believe in rotary degassing, that rotary gassing not only removes hydrogen, but has a direct effect on inclusions and oxide. And in the past, especially in high pressure die casting, many people disputed that. Many people in the industry didn't believe that rotary degassing would have an impact on their melt quality. And when we went one step further and we applied our MTS technology to this foundry, which is the green column there, you can see an even further. So the MTS has taken the melt treatment one step further, and you can see how the total number of defects is reduced and how the total number of oxide and inclusion is reduced. So this is really a very nice quantitative way to show that not only rotary degassing, but people who do flux injection, people who do melt treatments, really improve the melt quality when it comes to making low pressure wheels and wheels. And today around the world, I think 90% of all the wheel plants that I've visited, and I've been to quite a few of them, are using some kind of MTS or flux injection or rotary injection because they know this will improve the melt quality of their wheels. We don't need to dwell on this one. This is the same one. It's in the paper where I show this on the graph. Okay, let's now talk about a very interesting example. This is an example in high pressure die
Mr.
casting.
Kientzler, it's time.
Okay, sorry. I know I speak too much. So anyway, so are there any questions?
Yeah, I think we'll have to go ahead with the questions. I'm sorry to interrupt you here, but
No, it's no problem.
you've given us a very, very, very informative and very, very gripping insight into the complete technology that involves the melting of aluminum for both high pressure and low pressure and gravity die casting. So thank you very much for your presentation, and we'll share the details once we have them in the presentation with everyone. Okay. So the house is open to questions. You know, there is one question just come on from Mr. Vashisht Kumar Tripathi. He's asking you, can you show some data on the comparison on molten metal purity in terms of the inclusions? So I think you have shown data, but if you want to answer this, it's open to you.
Yes, let me, oh, now I've lost the, hold on. Can you still see my presentation?
Yes, yes, we can.
Sorry, so let me switch to the last one. This is the one. We went to a chip melting operation, which was making ingots for the foundry using 100% chips. And this is a VMET analysis we have done, where we took a sample from their melting furnace after melting the chips. And I could not believe how many oxides and inclusions we found. So these are the number of oxides inclusions found in, so the yellow, the purple one is one melt, the red one is another melt coming from two different furnaces. You can see that, for instance, chip melting creates billions and billions of oxide. I mean, it's really something that's absolutely incredible. Here is the same data, which shows you the number of aluminum oxides in the, so what I would say is those people, and of course, many people in the industry are aware of that, the people who remelt chips, even if it's only 20% of their machining chips, whether it's in high pressure. I visited many very large foundries, you know, this is becoming very popular to save money rather than selling out the chips, the machining chips. Many foundries in Asia are now buying melting furnaces to try to remelt the chips themselves. And this is becoming very popular, both in high pressure and also in low pressure, and sometimes in cylinder head in gravity. Whenever you generate large tonnages of chips, and what I would say from this study we have done, people have to be extremely careful how they melt the chips, because you can see that if you do not melt them properly, if you do not submerge the chips in a dedicated chip melter. Now, we don't have this, but there are furnace makers in India, in China, in Europe, who have developed chip melting furnaces, you know, specific furnaces that enable you to remelt. So I would always encourage the foundries to talk to these people and to invest into a real furnace that is designed to remelt chips, not try to throw 30% of chips in their own melting furnace, because it can really mess up their melt quality. It can really dirty the melt if the chips are not properly melted. And this is what this last case has shown with this chip remelter.
Thank you. So there is another question, I mean, which is from my side and also my colleague, Mr. Sripath Kate. He's talking about the new MTS 1582 that you have introduced for the wheels in the LPDC process. Now, yes, is this also suitable for the GDC process where we have a continuous melting and where we are using alloys such as A356 for chip melting? Is
yes,
this process usable there?
Yes, sorry. So I can answer you. It is suitable. And in the references of my paper, I think one of the reference, my colleague from the US has published a paper together with a foundry where they have a continuous melting casting furnace where we're using this. So if you look at the references of my paper, is Brian began, and I think it's the last reference in my paper. There is a paper about grain refining with this MTS 1582. Yeah. So my answer is yes, it's suitable. And we have already published one paper on that. I hope that in Asia, we're actually looking for other foundries that are willing to work with us so we can publish more papers on this subject.
Thank you. So one more question from my colleague, Rajiv Chandel. So he's wanting to ask, can you suggest a flux for the degassing of the ENAC 443 and ADC 6 grade alloys? You know, any specialized flux that you would recommend?
Oh, that is, look, this is, I would ask you to forward that because I'm not familiar with that alloy,
all
like
right,
off my head. So could you please forward to Shrikant Bhatt, you know, to my colleague from India,
okay,
and then we will discuss this.
Sure, we'll do that. So is VMET commercially available for the foundries with SEM? Is a question that's come from Vivek Joshi.
Okay, VMET is an internal. So originally we developed VMET to evaluate our own materials in our R&D labs. So VMET is not something you can buy, you know, in industry or from a supplier. VMET is a technology we developed internally to investigate the defects in the materials. And so what we have done is, rather than look at, I don't know, ceramics or steel or iron, we've applied it to aluminum alloys. So this is really a proprietary technology which we have developed in-house. But if foundries are interested, you contact Foseco India, Shrikant Bhatt, my colleague,
okay,
and we can do VMET evaluation with foundries who wish to do that, okay? So if they have specific problems, we are allowed or we are able to take samples from, and this we can do in partnership. This needs to be discussed directly with Foseco India.
All right, thank you. And I think this would be the last question, just come from our COO, Mr. Kaushik Manna. So he wants to know, how do we get a uniform mechanical property at different locations and parts of the alloy wheels? How do we ensure, and how do we do that?
Oh, that's you mean in the casting itself?
Yes.
It depends. Okay, it's complicated because so the mechanical properties are impacted by the cooling rate. So the cooling rate depends on the machine you use, but also on the thickness of your casting, you know, and the parts of the wheel are thicker than other parts. The hub, for instance, or the spoke is usually thicker than the rim of the wheel. So the thickness of the casting and the cooling rate of the casting makes a big difference. It's not just grain refining. So grain refining is a given, it's needed, but then, so usually, I mean, I cannot, this is a very complicated subject, and if you want, this is something we need to discuss outside of this forum, because there is no answer.
Dr. Kientzler, I mean, you said it depends on the cooling rate. Can you just give us the equation? Is it directly proportional, inversely proportional?
I don't know, because wait. There are different technologies for low pressure machines, okay? You have European technologies for low pressure machines. You have Chinese ones. You know, you have different manufacturers in the world, and the cooling they use, whether it's water, some people even use air, but I mean, that's almost gone now. Now it's all water. But the way they do the cooling, this depends on their equipment. This is more depending on the equipment that you buy from the low pressure machine manufacturer than on anything else, okay? So I am not able to comment on that in such a simple way.
All right. So thank you very much, Dr. Kientzler, for a brilliant session. And I would now hand it over to Zubin Kabraji for his comments and for beginning the next paper.
Thank you very much.
Thanks.
Thanks, Philippe. Thank you, Tej. I just want to take a minute just to welcome Mr. Vivek Joshi, the president of Sundaram Clayton Limited. Thank you very much, Mr. Joshi, for being present. We are very honored to have you here. Sundaram Clayton is an associate sponsor, and it's a great privilege to see you here. Thank you very much, sir.
Dear Mr. Kabraji and entire aluminum casting community, Tej and team, thank you very much for having me here. I am also honored to be part of the community, always available for the team. Thank you for having me here.
Yes, thank you very much, Vivek. Great to have you. Great to reconnect. So I think we move on to the next technical paper. So this one is on a very favorite subject of mine, applying the advanced dye lubricant technology for true cost savings, presented by John J. Belyk, Business Development Director, Diecast Chem-Trend Limited. The paper speaks about the die casting industry going through a lot of developments, increasing part complexities, newer alloys to replace steel, and productivity needs for the demand of dye lubricant differentiation. Chem-Trend would help you to understand the need for an optimized dye lubricant for every application. The insights will help you to choose the advanced dye lubricant technology by Chem-Trend with focus on true cost savings by productivity improvement. And to speak of John Belyk, he's been a very old timer in the lubricant with Foseco, with Chem-Trend for a long time. And he's been a presenter in the ALUCAST for quite a few instances. He's the Global Business Development Director for die-cast industry at Chem-Trend. He has been with Chem-Trend for 27 years and has garnered depth and breadth of process chemical specialty expertise that spans multiple industries and applications. John holds a bachelor's degree in business administration and started in Chem-Trend's operation group in 1989. He then moved on to the technical services for the company's polyurethane rubber composites tire business. He went on to become a sales representative for Chem-Trend's plastic and rubber division with South Central region of the US. In 2000, John moved to Chem-Trend's die-cast division as a company sales representative to the Canadian market segment. John embarked on his first management role for the organization in 2005 as field sales manager for the tire industry, with a position as sales manager for polyurethane following soon thereafter. So John rejoined Chem-Trend's die-cast team in 2011, stepping into his current role as a die-cast business development director. As such, John provides strategic direction for the company's global die-cast product line through leadership of Chem-Trend's technical team. So that is what is about John. So I request John to take on the charge for the presentation. Over to you, John, and welcome.
Excellent. Thank you very much. Try to share my screen here.
Yeah, we can see it. Oh, it just got over. We are able to see it. It's not there.
And there we go. I think you have it there now,
Yeah.
right?
Yeah, correct. We can see it.
Excellent. Okay, thank you very much, Tej. And, Mr. Zubin acknowledged you for keeping everything on track yesterday. I'll try not to break that streak for you, sir.
We're still maintaining that, yeah, that's right.
Yeah, so thank you to the ALUCAST committee and organizers, and for everyone here who's participating in the conference. I appreciate your time. Before we start on the whole COVID, I just want to put my best wishes out there to the Indian community. Unfortunately, statistically, someone that is out there has probably been touched directly by the COVID, and unfortunately, probably in the worst of ways. So thoughts and prayers are with everyone. I really miss, being there. I wish we were all together. A lot of friends in India, and I guess I was a little bit homesick almost. So I look forward to as soon as we can get back to the normal, and I can shake everyone's hands, and we can have meals together again. So with that said, let me get into the presentation here. So talking about dye lubricants, true cost savings. I think when my colleague Vishwanath had asked me to talk today, I really want to do it more on an education level. Talk about what we look at to make sure we're focusing on the back end, of the casting process. But before I get into that technology part of it, I'd like to talk a little bit about, what drives us as, release agent manufacturers to improve our technology. And the first there, it's always been there for a long time, increased focus on productivity. And for die casting, it's historically been make things faster and hotter, just controlling that thermal part of the process. Can we kick parts out? And that's still the case now, but it is changing, as I'm going to talk about when we get to some structural discussions. But another aspect that's always been there is reduced waste. Obviously we want to improve our efficiencies, reduce scrap and rework. But another one that's coming up a lot more is plant effluent and water. Back in 2016, I did present a paper here to ALUCAST on water conservation. I think it was 2015 when the really significant drought hit and hurt. So obviously, any conservation we can do is better for everybody as far as water goes. But tooling cost is also there on waste. And then complexity. These net shape castings that we're making today, highly complex, and that really puts stress on a die lubricant. We have to make sure those parts fill out well, release well, and that can be a real challenge. So it's charged us to step up our game, in our technology. But now, let's camp out here a little bit. E-mobility. E-mobility is definitely changing. I remember, if I go back about 8 to 10 years, when we started talking about the effect that e-mobility is going to have on die cast. We're so reliant on internal combustion engines and transmissions. And there was a big fear that e-mobility was just going to crush die cast and composite parts were going to take over. But in reality, we see it as an opportunity. This lightweighting movement, even before e-mobility, just to extend the range of vehicles, lightweighting is taking off in a way I wouldn't have imagined 5, 6, 8 years ago. I remember when the first structural parts were coming out, and it was the new thing, but now it's becoming commonplace. I know there are some casters in India that are starting to get into this. They're investing in some machines, and it's going to happen. I mean, it's a wave. There's no doubt it's heading this way, and this has really had a major impact on our business and our technology, because these alloys, they're pretty aggressive, and I think I'm going to go and talk about that. Yeah, so the structural alloys. They're obviously low iron alloys to get that ductility that we're looking for, and they have a high affinity for solder. So we really have to provide better protection on the die with our lubricants for these applications. I already talked about net shape castings, but these castings now, what used to be so many stamped and welded steel components into a net shape casting, they're getting extremely complex and large, as you all know. I mean, the castings are getting really large, really complex. So we have to have great metal flow and good release characteristics. But another big part of this, and this impacts all casters that paint parts, but this post-cast processing. We look at these castings specifically for e-mobility because they're lightweighting, they need Class A surfaces, but a lot of these castings are going through cathodic coatings, welding and bonding. It's amazing how many parts now are actually glued together. So we have to make sure that the release agent film that's on that casting after it's cast can be removed so the part can be painted or bonded or whatever it may be. And that is a little misnomer. You may hear people talk about a paintable dye lubricant. It's not really that dye lubricants are paintable. The dye lubricant chemistry has to be cleanable so they can be painted. And that's usually done through an alkaline cleaning process. We've got our sister company, Surtech, who's always there to help us or help the industry if there's any issues with that. But when we troubleshoot problems there, it's typically in the cleaning process that we have to attack. But all this, as I've talked about, really requires differentiated technology, whether it's a conventional diluted dye lubricant or what we would call HERA. HERA formulation for Chem-Trend, it's high efficiency release agent. Also, you may know as water-free or a micro spray. Obviously this is going hand in hand with these structural castings and all the tooling technology that's coming along with it. Once again, just what we're seeing in tooling with additive manufacturing, it's really changing the game and changing the way we need to approach our chemistries or our technologies when we develop products. So it adapts and provides the optimized performance for a caster. So like I said, I gave a presentation at ALUCAST in 2016, and I talked about dye lubricant functionality and what we measure, what a dye lubricant is supposed to do for a caster. And I'd like to just retouch on that because I think, here again, the education aspect of it. Education is important. And the more the community understands what we're trying to accomplish as a supplier in getting technology out, the better you can use it for improved productivity. Dye lubricants, obviously, we need to release a part. It's often called a release agent. We use the term dye lubricant and release agent hand in hand, but we release parts and we also do lubricate the moving components of the dye. At the same time, we have to provide a good barrier coating for the dye, for your solder protection, your erosion, everything that comes with that. But you may not realize it, but the dye lubricant selection can have a huge impact on metal flow. So when we're talking about castings that have deep draws, some of these structural parts, we've got to get, you've got to get that metal in there. It's not all heat. A lot of it is what the cast or what the dye lubricant imparts upon that surface of the dye that helps you fill. It's a flow promoter. Surface quality, obviously, good castings, bad castings, dye lubricants can have an impact on that. But historically, the number one thing that it really gets used for is a bit of a crutch if you don't have good internal cooling, is thermal balance. And that's where we can really bring efficiency to the process, for improved cycle times, lower usage. And here again, that's where the water conservation and waste streams comes into play. I don't know of anywhere globally where water, waste streams and water conservation is not an issue. Of all places, China is really cracking down on that now, putting a lot of heavy regulations on their casters. So if we can be more efficient with our lubricants, less they use, and less waste stream. Here again, that's where the HERA, the high efficiency release agents, also come into play. And the other one for dye lubricants is dilution. And I do want to touch on this a little more. Some lubricants will give higher dilution, but this is where I have the biggest concern. Is I think often casters go for a high dilution lubricant. They excessively dilute the dye lubricant with the belief they're saving money, when in all reality, it's having a negative impact on their productivity. And what's productivity? I mean, you make money by getting castings out the back door, off the shipping dock, and doing that as efficiently as possible. And that's one of the things I'm going to key on in the next couple slides. But improve dye life. Dye lubricants have to protect the dye. Solder erosion protection, carbon buildup, they all play a part together, and ultimately for component quality, which we've seen them all. We all know the casting defects, but part integrity, when we start talking about structural castings, porosity becomes very important there too. Because, unlike an oil pan where the concern point is some oil dripping on your garage floor, when we're talking about structural castings that are there to provide crash safety, replacing these steel components, porosity is really key, especially when we're talking about welding castings too. If we have porosity in the casting that we're going to try to weld, that's a weak point. So, the dye lubricant and the proper usage of it becomes very key with that. With that said, I do want to touch on one thing. Is all of this, for Chem-Trend, falls under sustainability. Sustainability is, some may see it as a buzzword. We take it extremely serious, and it's always been part of our business model, specifically for die cast. Because what have we always tried to do? Anyone who knows me, I've come in, if I've given a talk in one of your facilities or, at ALUCAST or wherever it is, I'm always talking about efficiency, trying to make things better. And what is that? That's sustainability. Now, when Chem-Trend looks at it, we look at it in two ways. We have what we call our footprint, which is what Chem-Trend does, in our manufacturing facilities. We want to have as small a footprint as possible on the environment. But when we talk about our customers, we're talking about our handprint. So how can we touch our customers and have an impact to help them? So we want to have as much handprint as possible. So when I talk about all this kind of stuff, I may throw that sustainability part out there a couple of times. So now let's shift over to chemistry and how dye lubricants work. Like I said, we're talking about cooling a dye. So when you try to cool a dye, we're talking about Leidenfrost. What that is if you ever have a hot pan on the stove, you splash water on it and you see the bubbles of water dancing around on the pan. What they're doing is that's the bubbles on top of these little, this vapor barrier bouncing around. And that is because of the phenomenon called Leidenfrost. And it's keeping that lubricant from touching the surface. If it doesn't touch the surface, it can't cool the dye nor build the release coating on the dye. That's maximized when we do cool the dye. It's maximized at a point called the Nukiyama point, which is where there's nucleate boiling and cooling. I'm going to go into a little more detail there. But when I talk about cooling, something I want to mention is it's not the lubricant itself that is cooling the dye. So it's not the liquid lubricant on the surface. It's when that lubricant evaporates. So the best analogy I can give is on a hot summer day when it's 40 C outside, you go swimming, you get out of the water and you feel a chill. What you're feeling is the water on the surface of your skin evaporating. When it evaporates, it takes energy with it. So it's latent heat of vaporization. So that's what actually cools. So sometimes people say, oh, I need to heat my dilube, I need to cool my dilube. You don't want to do any of that. You know, the dilube is effective in cooling when it hits the surface and evaporates off of that surface. Which, you know, taking the technology discussion a little deeper, here's a chart, which is the boiling curve. And this one reads from right to left for surface temperature on the x-axis. The y-axis is heat flux, or the rate of heat extraction from a surface, or from, you know, from whatever it may be. So if we talk about dye lubricant and we start spraying a dye lubricant on a hot surface, we do not extract a whole lot of heat. I mean, this little orange part could be up or down, but we're not extracting heat until we break through that Leidenfrost point, which is transition boiling. So what that is when it finally breaks through, that droplet of water and lubricant hits the surface, it explodes. And when it explodes, that liquid evaporates from the surface and takes that heat out with it. So it starts to cool. So what we have here on the chart is when it starts to cool, you know, starts to rapidly cool the dye, and it's maximized at that nucleate boiling point. So that's when we get our maximum cooling, and then it starts to drop off from there. It's still cooling, but not at the same rate. And when we get through this, if we look at this gray line down here in the bottom, that's building our lubricant film, which is the secondary y-axis. So once we start breaking through that Leidenfrost point, we start to explode on the dye surface, start to build that lubricant film, and it builds up through until we hit this wetting zone right here. So now what I'm going to show, and hopefully this comes through well, is some animation. Oh no, first, okay, so what do we do? I'm sorry. What do we do to improve this? Anything we can do to help this happen faster at a higher temperature makes us more effective. So we speed up the process. If we can shift this whole chart to the right, you know, that's where we have our impact. Now I have some animation I'm going to show that hopefully will make this a little more clear. So we're spraying a surface, and what it's doing is these droplets, they're on the little arrows here. That's that Leidenfrost phenomenon, that vapor barrier. So we're not breaking through it, and the droplets are bouncing off until we hit this point where we overcome Leidenfrost. And we start getting that explosive boiling. So the dye starts to cool at that point in time, and it's maximized when we get these droplets that'll stay on the surface and boil, nucleate boiling. And that's where we really start to get a wetting and spreading of the dye lubricant across the surface. So that's where you're building your protective film. All right. Now, for years, I hear all dye lubricants are the same. You know, I go and say, no, there's no difference. Well, what I'm going to show you now is a laboratory test. And when we look at this test, what we do is we start spraying a lubricant. We've got two different lubricants here, both Chem-Trend lubricants, and we spray water. And we're going to build this cooling curve. So we start spraying at a nice high temperature around 430 C. And you'll see that as these materials spray, they hit the Leidenfrost point, and you can see it. Once you hit that point, you get dramatic cooling. You can see here in the white one, especially Chem-Trend B, it hits the Leidenfrost point, we get dramatic cooling. So you're going to watch this get sprayed. And once again, this is a laboratory test. So to be clear, I'm not saying that if you start spraying a dye that's 425 degrees with dye lubricant A, and if you spray it for 10 seconds, we're going to take you down to 325. This is a relative laboratory test. But what I will tell you is a difference like this has a significant impact in your process and your spray time. So, okay, here we go. Need to pause this for a minute. So upper left-hand corner, there's a chart. If you could focus on the lower left-hand corner first, this is the higher heat extraction dye lubricant. And when that hits the Leidenfrost point, you'll be able to see it. And then we're going to shift our view over to the lower right-hand quadrant to see the second dye lubricant. So here we go. There we go. You saw when we hit that Leidenfrost point. All of a sudden you can see that film. Now let's look on the right. There we go. We broke through Leidenfrost and look at that dramatic cooling. And now we wait for water. And there we go. Water hit the Leidenfrost point. So if we come back to the chart, you know, a couple of takeaways from this. Okay, there is difference in chemistry. You know, what you saw there and that is fully intentional. Typically, we're looking for a faster working, higher heat extraction material, but not always the case. If you have some very thin wall castings, say electronics, we're making cell phones. Do we want this kind of heat extraction? Not necessarily. We need to get the film formation, but we don't want to take heat out of these dyes because we don't, you know, it's all thermal balance. It's energy in and energy out. So, you know, we've got to keep that in balance. If we take out too much out, also we have a cold dye and we're getting all those cold dye defects. But the other point is, if you look at this, when used as designed, you get high performance and differentiated performance. Of course, if you take these and you dilute these, over dilute these with water, you take your dilution way high, more water, what's it going to do? It's going to perform more like water. So you take a dye lubricant that's intended to perform a certain way, over dilute, and all of a sudden you have the performance of water. And you all saw in this cooling curve, you know, that's a lot more spray time. So it's wasted cycle time. It's a lot more waste, plant effluent going out, a lot more water usage. And on top of that, you're probably not building the best film possible. And I'll come back to that in a moment. So here's a real world example. If we look at the section of images on the right, thermal images, we look at this zone A, had a max temperature before spray. So, you know, it's before spray of 377. After spray, it went down to 244. And this is a set spray pattern, set dilution of product. Everything's the same. The only thing we changed is dye lubricant technology or chemistry. So if you go to the high heat extraction dye lubricant, that same process went the max 364, and then after spray all the way down to 218 instead of 244. So I don't know if you can all see me, my video, but you know, it's all thermal cycling. You know, you make a part, you spray your dye lubricant, take the dye temp down, you inject that molten metal. It's all here again, energy in, energy out. That energy from the molten metal is absorbed into the dye so the part can solidify, right? The dye opens up, you eject your part. What do you do again? You spray dye lubricant on it to cool the dye down, so maintain that thermal balance where you need it. In this case, what we're able to do is with this higher performing lubricant, we could cut our spray time. So it went from 244 down to 218. So what do? Everything the same. We cut our spray time, whatever it may be, 10, 20, 30% to maintain that thermal balance. But there's another aspect of this. Depending upon the technology used, it may perform better at a higher temperature. And that was the case here. So instead of targeting a 244 degree post-spray temperature, with the higher performing lube, we would take that up to 275 or 300 degrees because the product itself was still effective in protecting the dye. So there's something about the chemistry on the dye surface that, is better for solder protection, is better for release and slip, whatever else you need, metal flow. And that's where another aspect comes into play is dye life. Once again, the entire die cast process is thermal balance, going up and down. I know there's a paper yesterday that talked about spray and minimal spray, cutting down spray. If we think about it, every time you cool that dye with dye lube and then eject another part, it's going up and down so much, you get a lot of compression, a lot of tensile stresses on your tooling steel. And what's that lead to? It leads to your cracks, your heat check. That's where the damage to your dye comes. So if you can get a lubricant that will let you spray less and lower that fluctuation in dye temperature and still get the performance, that's less stress as you're putting on your tooling steel. That's one thing I've talked about this quite a bit. And then the whole concept of this microspray comes up, and everyone get really excited about microspray for good reason. There's absolutely no doubt, for good reason, because you're controlling your dye with internal cooling, additive manufactured cores and such. So you're not putting those stresses on your dye, but you can make those kind of improvements without going all the way to a Hera or a microspray product. Getting a high performance lubricant, you can do that. You can make improvements on there. One final point on this is that often if you'll run a trial with putting a higher performing material on it, if you try to just start running that trial without changing any process parameters, it's going to fail, because we get so much more cooling. Then you're going to go down, you're going to get more porosity because the dye is too cold. You're not going to have shiny parts. You're going to get more staining. So it's all about getting the technology in there to optimize the process. Okay, dye adhesion. So when we spray a dye with different or with a lubricant, we talked about Leidenfrost. So at the high temperatures, if you spray a set amount of dye lubricant, only so much is going to adhere to the dye. Obviously, as the dye temperature goes down, you get better adhesion because you're not fighting against that Leidenfrost so much, correct? Okay, so when we look at technologies for dye adhesion, different generations, and we don't really go by this anymore, Chem-Trend, but we have different generations of silicone technologies. And as you can see, as we move through generations, not only did we get better dye adhesion at higher temperatures and lower temperatures, but we were able to incorporate in the ratio. So it's more effective at both temperatures. Now, when people look at this, they say, what's going on with that one that you have marked Gen 3? Here again, more adhesion, more cooling isn't always better. In this case, this was developed for a very large caster because we developed the silicone for one customer. But they wanted certain properties, performance properties in their lubricant. So, that's why that was developed, and that's why it looks a little off, out of place there in that chart, but it was purposeful. Final point is wetting and spreading. Obviously you can't spray every bit of your dye. So if a lubricant wets and spreads well, what that does is, it'll work its way into other areas of the cavity where you maybe didn't get a direct spray. So that really helps with a consistent film. But what that also does is that impacts your solder, your metal flow, die cooling, because you are making sure you get that consistent film. And here again, we can look at any one of these properties. We can focus just on cooling. So I could provide a dye lubricant that gives the best cooling you ever saw and the highest dye adhesion. But you know what? It might also give you the worst buildup you ever saw in your dye, which leads to plugged vents and porosity and everything bad that goes along with it. So it's really about we choose our components purposefully in order to get the right balance for a product and for a process. Okay, I don't know if Vishwanath, my colleague, Vishwanath Ramakrishna is
Yes.
online. Okay, and he was going to
Yes,
talk
I'm here,
about some case studies. And Vishwanath was recently just promoted, moved into a position of industry development manager for Chem-Trend for all of our diecast India. So this is my first time online with him to congratulate him publicly. So, okay.
Thank you, John.
Here we go.
Yes.
Yeah, welcome, Vishwanath. You have 5 minutes for the presentation because we also have some answers.
Thank you very much, the ALUCAST team. Thanks, John, for that wonderful, insightful presentation on the diecast dye lubricant technology. And just want to show to the entire crowd that when we develop these technologies, where have we applied all these? And, we had some challenges. The customer was facing some challenges. We partnered with a global tier 2 automotive component supplier who was making large transmission castings. They had a lot of cost pressures, productivity issues due to frequent polishing, decreased dye life due to excessive polishing and the erosion of the dye surface. They had also had increased consumable cost, which probably most of us ignore because we are ready to polish the dye, but we also don't add a cost to these consumables. And with all this, the cycle time increased and the customer was not able to meet their schedules on time. So we had a detailed process analysis of the whole process, and we ended up in reducing the cost on the consumables, improving. We used low buildup, high temperature, wax-free dye lubricant technology, which enhanced the solder protection on the dye. And in turn, the customer from 2 hours, they were polishing every 2 hours, and they shifted to 8 hours a day. So a significant improvement for the customer. And they ended up, because they used to stop the machine every 2 hours, they had a lot of startup issues, adding castings to the scrap, and which eventually increased their cost. So when we increased, their time of the effective usage, we reduced their scrap, and we helped them optimize their dilution, optimize their spray cycle. The customer ended up saving about 1.4 million rupees on one machine. So this was a huge cost saving for the customer. Over to the next one, John. Here's another case study from the US, one of the largest die-cast facilities there. The customer had very high scrap rate, higher downtime, extremely high die phase buildup. Then thanks to our technical experts, our sales guys back in the US, who had a detailed process study and understood that the issue was due to the low performing dye lubricant, which the customer had to run richer, that is lower dilution, which actually choke the dye lubricant lines, the spray cassettes. So they had to come up with a new formulation, and the Chem-Trend R&D helped them in new optimized dye lubricant formulation. The customer was very happy because they saw a 54% reduction in the cleaning time, the amount of time they took to clean the dye surface, because they had to keep the dye clean for having a very good locking force. And they reduced their scrap rate by around 1.4%. On all this, and the customer was very happy because we provided a very consistent surface finish, improved part release, reduced their inventory issues because we reduced the scrap, rework, and downtime. So this is how, when we make a dye lubricant, we apply that on the field, help the customer save more money. This is what we intend to do for the customers. Over to you, John.
Okay, so this final slide, I think the timing came out perfect. Shocking myself, to be honest with you. But it's just a summary slide. We like to focus here again, focus on productivity and part quality. What's going out the back door. That's where the profits really come from. And I just get, I'm pretty passionate about it. I like to see the lubes used as designed, and I know we can help people when we do that. So with that said, would welcome and appreciate any questions you may have.
Yeah, thank you, John, and thank you, Vishwanath, for a very insightful, presentation on the dye lube. It's been a subject that has been, discussed times and over again. It's an endless subject for improvement. There is always scope to keep improving. I've seen almost like 3 generations of the Chem-Trend dry coats that have been used on various applications. And the general question, that is from my side, is when you sell a product or a dye coat, you actually don't sell a product, you sell a solution to the your customer.
Yeah.
So there are 2-3 things that come in. It's the quality of the dye steel, it's the quality of the surface treatment of the dye, and then finally the coating that you do, so it's a combination of all these 3 that ends up to give you a good release of the component or extended dye life. Like you mentioned, there is an issue, which is in discussion always regarding the heat crack and the thermal fatigue of the dye because of the cyclic cooling and the heating of the dye. So you mentioned, but there is a big discussion on how do we, kind of conclude on that. And is there any solution that Chem-Trend has come up with, like we've been discussing for a long time, on the powder technology for coating, powder spray technology for dye coating?
Yeah.
And according to you, the impact of the release, how much of the dye coat would you attribute to the cooling, the surface cooling, and the release? Do you consider them to be 2 different aspects of the same dye coat, or do you think it should be a combination of both? If yes, then which one impacts, or which should impact higher, or what should be the requirement?
Yeah. Okay, boy, let me try to get all these. Yeah, on that last one, it's their individual, quite honestly, for release and cooling. We'll use different formulations when we need high release. Sometimes they aid with cooling, sometimes they may hinder a little bit. It really comes down to having the right balance on both of those. Sometimes we'll have too good of a cooling and parts will stick on the die because it's a mechanical stick because they'll shrink. As the casting cools, it compresses, and you'll see that. So it's really a matter of balance on both of those. What you talk about, and I'm seeing some questions come up in chat, as far as cooling goes and the heat check, that's a sliding scale. There's a worst case where you're spraying a tremendous amount of dye lube to cool a dye because you have to rely on it for internal cooling because it's a crutch. It really is. So you get that. And like I said, going all the way to the micro spray. And you mentioned powders. yes, we have powders. We sell a lot of powders, but the liquid mist, so the micro spray or our hair, a high efficiency release agent, is really becoming more popular because it doesn't require electrostatic. There are some electrostatic ones out there, but if you go with water-based, it doesn't smoke. Still a concentrate you're spraying. Doesn't smoke, doesn't require electrostatic, and we can actually build some more technologies into there. But that's the direction that the industry has gone instead of powders. I think powders were just too complex in getting them to apply right. It really, when done well, it works really well, but it is hard to do in a big equipment investment. I see a question, can we eliminate dye cooling? We have thousands of casters out there that have no dye cooling and they use all dye lubricant. It's tougher on the dyes, but here again, it depends on the parts. How much do we have to take out? Once again, it's a thermal balance. If you don't have any dye cooling, you're making a transmission case, yeah, your dye life is going to be awful. If you don't have any dye cooling, you're making these little small components, that are grams, that's easier to live with because it's not such a stress on the dyes. How do you cool the dye if you use powder technology without water? You don't. Yeah, that's the thing. So if you want to use Hera, high efficiency release agent, or a powder, you have to count 100% of your dye cooling on internal cooling. And that's where, right now, the big new move there is additive manufactured cores, because they could put such incredible conformal cooling in them. Then we're putting on truly a release agent in those areas because you don't need the dye lubricant's cooling function. You're using it for all the other functions. And then what's your recommendation for uniform dye lubricant surface? PVD coatings and you know what? It stays the same. Those as far as our technology goes, they go hand in hand. We've done quite a few studies looking at the cooling rate of PVD coated dyes and non-PVD coated dyes, and it's the same. If they're still hot dyes, we still need to cool them because once again, that coating is such a microscopic coating. It's so thin, it really doesn't act as an insulator. It doesn't make a change there. So, it still relies on the same functionality. Liquid mist sprays, yeah, that's our Hera. So liquid mist sprays, and that there, yeah, that is that would be high efficiency release agent, a micro spray. Let's see, micron. We haven't really measured microns. We find that it's pretty flexible. The key is getting a nice light coating. So when you're doing something like that, I like to use the analogy, instead of using a super soaker like we do spraying dye lube, you're trying to paint the dye just like you paint a car. So you want a super light coat. I mean, it typically depends on the configuration of the casting. When you go to a micro spray, we're looking at a 0.5 to 1 cc per kg of casting weight. So very, very small, but I'll tell you what, as important as the dye lubricant technology is, the application technology is important too. You have to have really ideal sprayers and set up well. That requires a team of people. You really got to work together in a partnership. Dye lube, spray technology, and the caster, in dye configuration, dye design. A lot of investment there. In the front gate dye temp, pressure sides. Okay, let's see. In front of the gate, the dye temperature, the pressure is high because heated dye coat will not withstand, which leads soldering and dyes wear out. Correct. And that's where what I've seen, when you're talking about the gate area, that's where a good spray of a more concentrated lube helps. Not too concentrated because you want the right cooling. But that's naturally the hottest area of the dye, right, that ingate that's also seeing the most abrasive forces, right through there, right through the gates, especially if you got like an engine block or something that's got a big boss, right, that's going right into. So You know, and there is somewhere where the dye lubricant technology can make a huge difference, is protecting those areas from solder and erosion. That truly is a chemistry, you know, that if I know you have that problem, I will choose a specific chemistry to try to address that. These are great
All right,
questions. Thank you.
Thank you.
Yeah.
Yeah, thank you, John. And last, remark or question from my side is, are you suggesting that the dye coats should be more customized to the kind of product or the dye that you are running, or you have one product which can work on every component?
No. Rare, you know, obviously we try to have a broad application range for any product. That's the goal. You know, my goal, I'm always trying to get one product in a facility, but when if we have facilities that are making small components on a 400-ton machine, and they've got a 3,500-ton machine or a 4,500-ton machine, yeah, we may have different materials in there for those two applications. You know, it really has to go by the component, but we try to, you know, my goal is I want a controlled product line and, you know, a broad application range.
All right, thank you. Thank you very much, John. It was a wonderful technical paper and session. And thank you, Vishwanath. And over to Someda.
Yeah. Thank you. I just want, once again, I wish the best to everybody. I miss you guys more than you realize. Take care. All right.
Thank you very much.
Thank you all. Thank you. Thank you,
All right.
sir.
Bye now.